Welcome to this biochemistry video on the tertiary structure of proteins. There are 4 levels of protein structure: primary structure, which is the amino acid sequence; secondary structure, which is a localized structures, which include things like alpha helices, beta sheets, some random coils, turns, etc. Tertiary structure, which is the overall structure of a polypeptide chain; and quaternary structure, which is the interrelationship between multiple polypeptide chains. Today we're going to talk about tertiary structure. So tertiary structure involves many bonds, and it's stabilized in numerous ways. We have covalent bonds, for example. Obviously, the disulfide or the peptide bond between the amino acids is the starting point, but we also have disulfide bonds that exist between cysteine residues, and those help stabilize the molecule. There are also several non-covalent interactions that occur within a molecule. We have hydrogen bonding between polar groups of side chains. We have salt bridges, which are basically electrostatic interactions, and those occur between between charged groups. And we also have hydrophobic interactions and van der Waals forces. Hydrophobic interactions drive a polypeptide chain into a conformation that's entropically favorable, and then from there, so that's a non-covalent interaction, not necessarily a bond. So hydrophobic forces drive in we'll talk about this a little bit when we talk about folding in a little bit, but it drives the molecule, the protein, together, and then as in the localized region, side groups on the amino acids can then start to interact, and including electrostatic interactions, hydrogen bonding, van der Waals forces, and those can then help stabilize the interactions between molecules, or between those molecules or atoms of that molecule. There are multiple types of non-covalent interactions. Should be a review from some previous discussions that we've had, but it gives a good reference point as to what exactly you can get when we talk about bonding in a molecule. And the top 4, ionic or salt bridge, hydrophobic bond interactions, hydrogen bonds, and van der Waals, those are the most common. We do have some pi bonding interactions that occur between phenylalanine, tyrosine, and tryptophan. And you can also get some others, but those are the main ones. So here we're going to talk about protein folding and the theory behind it. And you can envision this like a funnel, where the energy state of the molecule is going to be driven down to its minimum. How does a protein get to a folding minimum? Well, there's a couple of important points. First off, a protein folds spontaneously and instantaneously during the biosynthesis of that protein off the ribosome. So almost immediately as it's coming off, it's going to start folding. There's 2 forces that take over immediately. The first one is the hydrophobic interactions. They're going to drive all the hydrophobic residues towards the center, and as it comes off the ribosome, it's also going to form its secondary structures. So those are the 2 main forces initially. And then what happens is the tertiary bond, as this molecule kind of folds in on itself, localized molecules will start to interact in a way in which it stabilizes the conformation and leads to its native state. So you'll start to see other forces take over at that point, in particular hydrogen bonding, electrostatic interactions, and van der Waals forces. So those 3 take over as soon as the initial couple of forces occur, and then you'll start getting also covalent where the disulfide bonds will take over. As this macromolecules fold themselves, there's a couple of important forces that also are going to influence folding, whether it's in a lipid bilayer or whether it's in a milieu. The pH and the salt concentration and the temperature also are important in how it folds. And last but not least, we also have chaperones that will help with this process as well. They provide a containment, and they're also there to eliminate the unfolded protein. That's the protein folding theory. And the main points in summary are: a protein will fold almost immediately off of the ribosome. It's instantaneous. The molecule will instantaneously start to do this, and it will start, and it will go based on hydrophobic interactions and secondary structure, and it will drive to a localized energy minimum. Denaturation is important as well because you're going to lose the activity of the protein. And this is not necessarily, in biology, if a protein is denatured, it's going to get recycled. And generally that's because it loses it's damaged of some kind. We can also do it with artificial or synthetic mechanisms. And some of those things are heat denaturation. And once it usually, if it's been if a heat source has been applied, it can renature back to its native conformation. This experiment was done with hen egg lysozyme. 6 molar urea. Urea is found in your urine, and 6 molar urea disrupts hydrogen bonds and can also denature a protein. Surface active agents like detergents such as SDS, tween, these also disrupt the tertiary structure. We can have reducing agents to reduce the disulfide bonds, things like 2-mercaptoethanol and DTT. They help reduce the thiol groups. You can add salt, heavy metal ions, alcohols. All of these can also help denature a protein if you need to denature a protein. So next we're going to talk about three-dimensional structures. And there's some important terms in this, including motifs. A motif is a supersecondary structure in which we have elements of secondary structure that are kind of put together. So some examples are a beta alpha beta motif. We also have a Greek key motif, a beta meander motif, a beta barrel motif. These are aggregations of secondary structure that appear. They don't allow us to predict the function of it, but they do have similar structures, and commonly they have very similar functions, but they can also have very dissimilar functions. It's because the relationship between our primary structure and secondary structure is not necessarily as straightforward as we would like. Motifs can be found in our recurring proteins and numerous proteins, and commonly proteins are held together by different motifs folded together. So commonly you'll see these all in the same protein. Some more examples is we have, an all beta motif where we have beta sheets that connect in a kind of a pattern. We can have crossover events. We can have right-handed connections between beta strands. We can have left-handed connections between strands. We can have twisted beta sheets. All of these things, again, there's numerous elements of these things this in particular are folds that you can find within proteins. And we also have these motifs can be added together to form even larger motifs. So we can build these up and eventually get into some very complex tertiary structures. So here we have a beta alpha beta loop that's made into a alpha beta barrel, which is a combination of all of these of multiple motifs. And in particular, this alpha beta barrel is important in things like pyruvate kinase, which is an enzyme we'll see later. Domains are conserved elements of a protein sequence, and they exist independent of the rest of the protein chain. So motifs are not necessarily independently stable out of the protein, where domains are very stable within a protein. So they form independent of the rest of the protein. And it's a compact three-dimensional structure. It's independently stable and folded. It can appear in multiple different proteins. These are commonly very similar in sequence or very similar with a lot of conserved residues, and there can be as long as 500 amino acids commonly. And here's several examples of domains. So what's the difference between domains and motifs? The motifs are not independently stable. Domains are independently stable. Motifs are usually a continuous sequence. Domains are commonly non-contiguous. Motifs do not have any similarity in functions. Domains usually have very specific, definite functions, and motifs can be part of domains. So if you have, and these are very technical terms when we talk about three-dimensional structure. So what domains and motifs are important for you to understand the difference between. Another element that's important in three-dimensional structure are intrinsically disordered proteins. In this situation, we're looking at very common ones, and this is an element that they can also become structured once they interact, or they can always just remain unstructured. And there's elements within things like P53, cyclin A, S100B, all sorts of elements within these proteins are disordered, and that doesn't mean they don't have function though. So they're relatively disordered until they need to bind, and then they don't assume a structure, but they do interact in a certain consistent way. So disordered proteins are very common, and they're also very common in the function of the protein. One other distinction that you'll want to know is the difference between globular and fibrous. A fibrous protein is non-soluble, so you can imagine something like hair, collagen, keratin. You can also have things like fingernails. They're very structurally oriented. Actin, myosin. That's a globular protein, or a fibrous protein. A globular protein is soluble in water, and that allows it. Those are the most common, but they're two very distinct proteins, and you'll want to know the difference between the two. One is very structurally oriented, fibrous, and not soluble in water. Globular proteins have a specific function, and they are soluble in water. Two ways to determine the tertiary structure of a molecule. First off, we have X-ray crystallography, and this kind of shows how an X-ray pattern is done. There's an electron density map that's created. This is an art form rather than a science, and so when we look at the PDB and some of these models that you can download off the PDB, most commonly these are X-ray crystallography structures created from X-ray crystallography, and it's important for you to. And this is what a X-ray diffraction pattern looks like in A, and then they build a model out of it, and they can get angstrom. They can get down to 1.5 to 2 angstrom resolution, but creating a crystal is not easy. The other way to do it is with NMR, and it's a little bit less common. You need smaller molecules, and you can do both solid and liquid. Both are very challenging. It's not a panacea. In fact, there's also very important size limitations in NMR, so it prevents it from being used in some of the large structural proteins. More commonly, it's used in determining the structure of peptides and things like that. Hope you enjoyed. We will look forward to talking to you in the next lecture.